My name is Tapan Trivedi and I am a senior assistant professor at Marwadi Education Foundation's group of institutions. And our topic of today's discussion is the closed loop control of induction motor drive with slip control. Now the outlines of today's discussion are closed loop speed control and slip controlled induction motor drive, where the current limit control is a part of the control mechanism, there will be a twist in between, and the problem will be assigned at the end. The outcome of today's session are that you should be able to understand the closed loop speed control techniques such as slip control and current limit control. We know that variable frequency drive are popular in industry, and the part shown here is a block diagram of closed loop variable frequency drive, where the PWM inverter provides variable voltage and frequency which is supplied to the induction motor. The speed is sensed through a speed sensor such as encoder. Now this applies the inner slip speed loop with the slip limiter. The slip limiter can be seen here, and for a given current the slip has a fixed value, so the slip speed loop also functions as the inner current control loop. Now it also ensures that the operation always occur on the portion of speed torque curve between synchronous speed and the maximum torque. So here we can see that the point of intersection shown are the point of operations. So when we start the motor, we can ensure that the same torque is maintained throughout the increase in the speed. Now the black one is the speed torque curve neglecting the stator voltage drop, whereas if you include the stator voltage drop, then there is a green curve. Now this indicates that at lower speed this will be dominant. Now the PWM inverter which is fed from the DC source has the capability of regenerative braking, right? Now the first is that the speed error is processed through a PI controller and the slip regulator. So whenever there is an error, there is a PI controller which will process this error and give the current as the output. Now the slip regulator will ensure that the maximum slip is maintained, and this way we can maintain the maximum current that will flow through the inverter. So the synchronous speed is obtained by WMS, which is equal to WM plus WSL. That means the speed which is the frequency which is given to the PWM inverter is decided by the original speed and the slip speed, and this determines the inverter frequency. So this is the quiz for you, that what will be the value of supply frequency if mechanical speed is 30 radian per second and the slip speed is 7.7 radian per second, assuming that the base speed is 1500 rpm. So let us think about it. We have 15 seconds. Okay, fine. Now we can understand that this is 30 radian per second and the slip speed is 7.7 radian per second. Now 1500 rpm is the base speed. That means at 50 Hz we will get 1500 rpm, which is near to 157 radian per second. So based on that, we will get the 12 Hz as the output. That means if you want to obtain 30 radian per second as the mechanical speed, with 7.7 as a slip, then we need to supply approximately 12 Hertz. Okay. Now as we can see, the speed is sensed through a mechanical sensor. There is a closed loop. PI controller provides the maximum slip, and then the mechanical speed is added to the summing block, which gives us the WMS. How to decide the voltage? So the voltage, the frequency is first given to the flux control. Now this is actually a lookup table or a function generator, where it ensures that the below base speed there is a constant ratio between voltage and frequency, and hence named variable volt per hertz. Okay. Now this voltage, as here it is shown as a straight line, so the voltage will follow linearly the frequency, but above base speed or above synchronous frequency, the voltage will be maintained, because we cannot increase the terminal voltage of the motor. So voltage will be maintained and frequency will increase, and that will result in the field weakening. Now this voltage, which is determined from the flux control mechanism, is given to this, and the actual voltage can be sensed, and then the voltage controller will take care of the actual modulation index, and modulation index is given to the PWM inverter. We can adopt any PWM technique such as sine PWM or SU PWM or any other technique to ensure that the modulation index is achieved. So what will happen when there is a step increase or step decrease in the speed command? Let us see. Whenever there is a step increase in speed command, it will produce a positive error. This positive error, because there is a large difference between the actual reference and the mechanical speed, so the speed controller will provide the slip speed such that it will saturate. It will saturate and it will go here in this portion. So the slip is at maximum. This slip is actually added to the mechanical speed, and this way we increase the mechanical speed or synchronous speed gradually. Hence, as we can see, the slip speed command is at the maximum value, and the drive will accelerate at maximum permissible current, because when the slip is large, the current will also be large. So by controlling the slip, we can ensure that the current is controlled, and that way we can achieve the current limit control. Now the drive continues to operate at maximum slip until the speed error is reduced to a small value. That means when the actual speed comes near to the commanded value, then the slip value will be confined in between, that is a linear portion. So the drive finally settles at the slip for which the motor torque balances the load torque. Now based on this, there is an exercise that what happens to the above drive when there is a step decrease in the speed command. Thank you. We will meet in the next class and we'll discuss what will happen if the drive, what will happen if there is a step decrease in the speed command. Thank you.
3.
Now let us understand what will happen with the step change in the speed command with this curve for a better understanding. So let us say our operating point is here, that is at this point, and we want to move at this point. Now if there is no slip regulation or slip control, then the drive will try to jump directly from this point to this point, and the command will also be set from here, that is this is synchronous pointed. So the command will also be set from directly here to here. If there is a PI controller, there may be some sluggishness, but still the current will shoot up. So what we achieve with the slip control, let us see. With slip control, we try to reach maximum slip, and that is from this point. We want to travel from this want to travel from this point to this point, but when there is a slip control, then we first go to the maximum slip, and then it will follow the command. Now of course there are curves in between which we have not shown, but the command will follow and the slip, maximum slip will be maintained. So as you can see, we are trying to reach to the speed with maximum slip, and now as it has reached this point, there is a difference between actual needed command and the needed command and the actual command. So now the slip is in the linear region. So what will happen, that the linear region will be activated and it will try to reach to the point, that is this point. So that means this way we can reach to the desired point with the limitation in the current. Of course there are advantages, but there are disadvantages also, that due to this the drive response may become sluggish. Okay, so thank you. Hope you will come next time with this analysis in the decrease in the speed.